This was a lot of details about cluster management. Now, let's stay in the same domain, and then both Michael and Nick from Hashicorp, they will cover how they do preemption in Nomad.
Hi everyone, my name's Nick, and I'm an engineer at Hashicorp.
Hello, I'm Michael, also an engineer at Hashicorp. We both work on Nomad.
We're here to talk about preemption with Nomad specifically. But before we jump into that, I want to kind of introduce Hashicorp for anyone that may not have heard of Hashicorp before. So we like to build software that helps teams deploy and automate their infrastructure and applications at any scale. And so we have a tool called Terraform that helps with provisioning infrastructure across public clouds, private clouds, and everything in between. Vault is a next generation security application that manages your secrets, your tokens, your credentials for all of your applications. And then Consul is a tool to help connect your services together via service discovery, service mesh, and service routing. But today we're here to talk about Nomad specifically. And Nomad's the runtime layer that will actually run your applications across your fleet. So let's just give an overview of Nomad. What is Nomad? So it's an orchestrator. It's in the similar domain as tools like Kubernetes, Mesos, Docker Swarm, Tupperware, and the like. And an orchestrator at a high level just takes your application and a description of its resources and maybe some constraints you have, and your fleet of heterogeneous nodes, and maps those applications to nodes in your cluster. And Nomad we want to make really easy to use for developers and operators alike. So to do that, we made Nomad in a way that it doesn't require some external state store. You don't need to also manage a database and your control plane. Nomad has a built-in, highly available replicated state store out of the box. And it's just a single binary. So one binary gives you can run it in client mode, which will actually run your workloads, or server mode, which does the scheduling and the state store management. It comes with a CLI and a web UI all built in as well. And my favorite feature is dev mode, which will spin up a single node cluster and a web UI and the CLI all configured to talk to that node. But we shouldn't have to sacrifice performance and scalability just to get that ease of use. So we have users of Nomad deploying with over 15,000 nodes in a single region. And we've seen numbers as much as, we have one user that's doing 5,500 placements of tasks every second on their cluster at peak times. And that comes out to be about 100,000 applications scheduled in under 20 seconds. And that's because Nomad's core scheduling logic is built on research done by the likes of Google from their Borg and Omega papers, and UC Berkeley from their Sparrow paper as well. And so we took it upon ourselves to do what we called the 1 million container challenge. You know, how fast can we schedule 1 million containers if we threw them all at Nomad? And so here's a graph of those results. And what really excites me about this graph is the shape of it. You know, as here on the y-axis you have the number of containers, and the x-axis is time. And the orange line there is when the task was scheduled, and the blue line is when it was actually started running. So after, in this case, Docker pulled the image and started running it. But this graph is almost linear. So as you scale up your application infrastructure, Nomad can handle that scale really well.
So performance is great. We all love performance. Bad performance is bad, good performance is good. But that's just one piece of it. We also really like features. When it comes to workload orchestrators, we would prefer to have one for all of our workload. It's just unfortunate when you have all of your new stuff in one place and then all of your old stuff kind of in a dark closet somewhere. So we built Nomad to support heterogeneous workloads. So whether you're using Rocket or Docker, or if you're deploying binaries or even just bash scripts onto your cluster, you can use Nomad for that. Likewise with architectures. That can be Windows, Darwin, Linux. And now we even support plug-and-play drivers if you have something either homegrown or something that isn't out of the box with Nomad. And we do this through a single interface called this job spec. So you're going to author your job using HCL. And you can see in this example, we declare what data centers we want to support, what type of job this is. Here we're creating a web front end. We want 5 instances of these things. So this is a template that specifies the work that we want to run, which is this task front end. We get the Docker container. We specify how many resources this needs, and then we're going to place 5 of them in the cluster. And those placements are kind of allocations. At the heart of Nomad is the scheduler. The scheduler is what takes those job definitions and actually turns it into running software. The nice thing about working with schedulers is there are a lot of real-world metaphors that we can use. So you can imagine if you're some sort of very important business type, you may have a lot of meetings with people and your calendar is really complicated. And it gets to the point where you can't really maintain your calendar and go to meetings at the same time. So you hire an assistant and they start doing that. And like honestly, if you have a good executive assistant, they're probably better at the calendaring than you are anyway. Nomad's similar. It's special case software that's better than you are at getting software running on hardware. At this point, Nomad has a variety of algorithms for placing software, but the primary one is bin packing. And as you can see in this example, just like how you're going to want to make sure that you're stuffing things in this drawer to make maximum use of space, Nomad's doing the same thing with your hardware. Instead of kind of just deploying VMs one-to-one on, or deploying containers one-to-one on VMs or what have you, we're going to maximize space to get you higher than like 30% utilization up to 80 or 90. But this kind of creates a problem. This is great because now you're spending less on your cloud bill, but it means that we now give you wings and you can fly too close to the sun and run into this new problem, priority inversion. And this is when you have a low priority task that's inadvertently preventing the placement of a high priority task. And we can walk through an example. So here in these green rectangles kind of represent your cluster and what's available. So the first thing we're going to do is we're going to place our web app. This can't go down. If it's down, our business is down. So it has a high priority. We place it, it takes up capacity. Next, let's run some analytics jobs. It has lower priority. It's still important, but it's not exactly mission critical. It takes some space. Now our email team has some marketing campaigns that they want to run. Sure, whatever, use our cluster. Now we're out of space, and the data science team still wants to run some stuff. They want to update their model. There's no room. Nomad can still take this, and it'll just be in a queued state. Once the email jobs are done, then these will run through, and everyone's happy. But then something unexpected happens. Suddenly we need to scale up our web service because we have a lot more traffic. But there's no more room. So what do? We have 2 options. The first, we can add more capacity. We can just provision more hardware. If we're fancy, we can even auto-scale this hardware. But provisioning more hardware takes time. Even in the cloud, it's going to take time. It takes even more time if you're on-prem and someone has to spin up a rack. The other option we have is to make something else give up its use capacity for our needs.
And so this is where preemption comes in. Now, preemption sounds really simple at the high level. You know, you have these higher priority tasks, and you have some low priority stuff running, and you want to boot that out to make room for the higher priority. But it turns out there's quite a lot of variables we need to consider. So let's walk through an example to try and enumerate those. So here we have some example job with a highest priority. And this box here represents a single machine with a whole bunch of tasks running already. And then the colors, the warmer tones are sort of higher priority and the cooler tones lower priority. So we want to place this somewhere on this machine. So there's a few things we have to think about. We have to look at the requirements of that incoming workload and that needs to be placed. And we also have to look at the resources that are running on that node. We need to look at the priority of the tasks that are running so that we, A, don't preempt higher priority work, and B, we probably want to start with the lowest priority thing possible and work our way up. But there's some other interesting things to consider, like the number of instances running on a job. Let's say you have a workload that's critical, but still something higher priorities coming in. You don't want to accidentally kill the last instance of that workload if maybe there's a deployment going on concurrently. We want to keep things healthy as best we can. And then you also want to avoid preempting too much and wasting resources. So you really want to find the best box to pull out of that cluster to put this one on. So this is sort of the first half of the problem. This is our allocation selection within a node. But we also have this problem of which node in our fleet to pick, because we could be running tens or thousands or tens of thousands. We're going to focus on this first problem to begin with. So we need to start looking at the invariance. So these are our hard constraints that must be met for this task to actually run. One of these invariants is job priority. Like I said, we don't want to preempt a higher priority workload. That defeats the purpose of preemption, so we can filter those out to begin with. And then we might have some static requirements. Like let's say this task needs to bind to port 443. It has a specific device it needs to use, a GPU. If we have a lower priority task that's running that's using those resources, we know that that is one allocation that needs to get preempted no matter what its resource usage or its priority. So now that we've kind of gotten these static requirements out of the way, we can start to figure out, well, what's the best order of allocations to start preempting. So let's start with a naive solution. Let's iterate through all of the possible combinations of allocations that are running on this node. That'll give us every possible situation that we could preempt. We could score all of these and guarantee that we have the best fit possible. But there's a problem with this. It's just far too expensive. Even on a node with 32 allocations running, that's over 4 billion combinations that we'd have to evaluate and score. So we need a different algorithm. In Nomad, we chose to implement a greedy algorithm that may not give you the very best fit preemption, but it will give you one that's good enough and it will run very fast. So the way this works, the first thing we do is we bucket these allocations by priority. It's kind of a natural bucketing mechanism we can use. So we start with the lowest priority bucket, work through those, and kind of work our way up priority bands until we've met those requirements. The next thing we need within that bucket is to know in what order should we preempt these in, what are the best ones to preempt first. And to do that, we need a distance function. So we have, we have some vectors or some dimensions on these jobs like RAM usage, CPU usage, disk usage, and device plugins bring more dimensions as well. We need a way to compare two tasks to see, is this one better than the next one? So to do that, we use like a Euclidean distance function or the sum of squares. We take each dimension and we take the resource needed minus the resource used over the resource needed. And that gives us a value between negative infinity and 1, where 0 is a perfect fit, and that's the closest that we can get to fit. So we take those and we combine those with that sum of squares, and that gives us the score for that allocation.
That was a lot of math kind of all at once. To help kind of solidify this concept, let's walk through an example with some diagrams. So here's a scatter plot. Each dot represents an allocation that's running on a single node. And what we're going to do is we're going to walk through all these allocations to figure out which ones we need to preempt in order to place the new incoming allocation. So first things first. At the origin point here, at the low priority and low distance, those are the best ones. Those are what we want to preempt first, right away. But unfortunately, we have to figure out our hard constraints first. So even though A10 is up in that top right corner and we wouldn't like to preempt it, we have to in order to satisfy the port 5656 constraint. But then we can move closer to the origin and start knocking out allocations that are low priority and have a low distance score. And we keep on walking until we have satisfied the resource constraint that we have. So at this point, we now have opened up enough space on this node to place our incoming allocation. But there's kind of one more component to this. We mentioned that this is a greedy algorithm. It's going to keep on preempting things until there's enough room. But what if we overcommit and we preempt more stuff than we could otherwise? So instead, what we do is we actually mark things, and then we come through and compact it, and then we preempt. So let's walk through how that's different. The circles have different radii at this point because even though the priorities and the distances are the same, different allocations are using different amounts of resources on the node. So again, we have to take A10 for the port, and then we can take A1, and you can watch this bar fill as we're freeing up enough space. Still not enough room, but A4 is a big allocation. At this point, we've overcommitted, so we can look back and see, do we need to preempt all these things, or are there some allocations that are marked for preemption that we can actually compact out of the way and still get away with placement? And we can. We can actually release A2 and A3 from our marking and only preempt A10, A1, and A4 and still place our allocation.
So like I said, this was just the first half of this problem, the allocation selection within a node. So let's talk about scoring nodes across your cluster. So we have this same example, and we have multiple nodes now. We need to figure out which one's the best one to select allocations for preemption on. And to do that, we sort of do two things. We use a heuristic that minimizes the priority of preempted allocations on a node. So we want to prefer nodes that have lower priority allocations running. But there's sort of a catch here. What we don't want to end up doing is preempting 100 allocations that are a priority 10, when if we just had another node, we could preempt 5 allocations that are just a little bit higher priority. So we want to sort of balance this score, boost it, or give it a penalty depending on the size of the allocations running. So what we end up with is 4 quadrants, something like this. You know, the dream is a node with really large allocations that are all very low priority. Better is, or slightly worse is a node with small allocations but still low priority. Getting worse with small allocations and high priority, and the worst of the worst being your node with large allocations and large priority. So those nodes before sort of fall in this range in this quadrant. Again, we pick the node closest to 0, which ends up being somewhere in this first quadrant. So once you've actually done preemption is all sort of done under the covers. Developers that are running their jobs on these clusters don't really need to know about it. But at some point as an operator, you're going to have to go and debug a problem, or you're going to have to go and debug an issue, and you're going to need some visibility into preemption. So the way we expose that is an allocation has a desired status state. It could be running, queued, things like that. So we added a new state called evict when an allocation is evicted. And then we added 2 new fields to its data structure. So you can know if you were preempted by another allocation, which allocation that was, or if you caused preemptions, which allocation IDs you ended up preempting.
Yeah, so as Nick mentioned, preemption's happening automatically behind the scenes, but there are still users, and there's still an experience. So we still want to think through the preemption UX. At Hashicorp, we have a driving mantra about workflows, not technologies. Workflows are what stick with us. Technologies enable them. And preemption is just the technology. So what are the underlying workflows? The first one is submitting a job. As a developer, you have software that you want run somewhere on your cluster. And you start by authoring a job in HCL, as shown earlier. And then you would run Nomad plan. So this will do a scheduler dry run. It'll tell you what the scheduler thinks needs to be placed. And now with preemptions, it'll also warn you if your job is going to preempt running software in order to make room for your job. And then lastly, you'll run it. So it ends up looking like this on the CLI. Nomad plan example.nomad. Scheduler dry run says, yes, I can place this, but there are consequences. This allocation needs to go to make room for your job. From the UI, it's going to look a little similar. So this is a contrived example with just a dev mode cluster that's limited to only 1 GB of RAM. But let's run a job. First thing we're going to run, and apologies for this being kind of small, is a batch job that has a high count and a kind of medium priority, but the resources are pretty limited. So each of these is only going to take 64 megabytes of RAM. When we go to plan this, the Nomad will say, hey, heads up, I can't place all of this. I can place some of it, but not all of it. It's a batch job, so whatever. It'll run through the queue. That's fine. So this is what that looks like. Some of it is running. Some of it's in queue. Next, let's run another job. This one, a higher priority service job. This one's going to take 512 megabytes of RAM. But our whole cluster is already at capacity with the batch job. So if you've done the quick math, that means we have to preempt 8 of these batch jobs in order to make room for our service that's incoming. Let's just go ahead and do that. So once we've done that, you can see now the high job at the top is completely running. And the batch job, the majority of it is still in that queued state, but some of it that was running is now in that darker shade of green that shows that it's actually now in a completed state because it's been evicted. Lastly, let's run a third job. This one, a low priority job. When we do this, dry run's going to say, I have no room for you. And it's also not even giving us the option of preemption because all of the jobs that are using our capacity are of higher priority. We can still run it. It just means it's going to be stuck in this queued state. So another workflow that we have is inspecting a job. So say you started that batch job, you went to lunch, and you've come back, and now you want to see what's up. And you said there's kind of an unusually high number of stopped allocations for this. Well, now you can observe that some of the allocations were preempted, and that kind of explains what was weird. And you can also click through to see what job caused the preemption. Or maybe you're sort of keeping tabs on a job that someone else started, and you can observe that that job caused preemptions, and then you can click through to sort of see the ripple effect that that had on the cluster. Or maybe you're not a developer, you're an operator, and you just want to make sure that nodes are up and everyone's happy. You can check out the allocations that are running on a node in your cluster, and you can observe that some of those nodes had allocations that are preempted. You could filter by just those ones and kind of investigate further. We can walk through that in the UI as well. Same cluster, same state that we left it in. Now let's click into this batch job, where we see an abnormally high number of completed tasks here. And we can see some of them are completed, and others are completed with this little boot icon that says, yeah, I completed, in that the cluster is no longer running it, but it didn't run to completion because it was preempted. And if we look at the detail page for that allocation, we can see this section here, preempted by. So now we can sort of click through to see what the preempted by allocation was and explore the state of the cluster. We can also look at allocations that had preempted other allocations and see the whole table. So just by looking at this, you can see that this is that high job that came in, because we saw the heads up that all 8 of these were going to be preempted. But maybe somebody else ran this and you're looking at it now. And in the third case, we want to look at the client nodes. We can click into one, and we can see down here in that little orange box the number of allocations that were placed on this node but have been preempted in order to make new, or to place new allocations. And as an operator, this might mean something to you. It might mean that this node is in high demand. There's something special about its configuration that people need, and that might signal to you to provision more nodes like this one. So we talked about workflows, but workflows are powered by technologies. Since preemption is fast, we can incorporate it into Nomad Plan. If preemption took upwards to 30 seconds, that would no longer be an instantaneous feedback that you get from Nomad Plan. And since the preemptor and preemptee allocations are linked in the API, we can make the UI navigable to open up these use cases for exploration.
Yeah, so preemption gives a way to keep your business critical applications running on Nomad, whether you need to scale up or scale out. So future work that we want to do, we want to improve this in many different aspects. One way is just improving the heuristic that we use to pick nodes in that multi-node scoring section. And we also want to expose some tunables of those to the user. Maybe you would prefer to weight your decision more towards a bin pack node than one that's not as full. There are multiple scores that actually go into your combined score, because Nomad has constraints and affinities and things like that go into it as well. And the other thing we want to do is rerun that C1M challenge. That data is from 2016, so it's been a couple years. Our scheduler's gotten more efficient, but we've also added more features to it. So we really want to rerun that again and be able to compare back those data points. So we've really hoped that you've found Nomad to be very interesting. And if you'd like to learn more, you can visit nomadproject.io, or you can view the source on GitHub under Hashicorp/Nomad. Thank you.